IT doesn't complain about my system utilization.
Missing one. Okay.
Nothing?
No, I just forgot to take a picture of something.
Oh, okay.
I was worried that I somehow forgot to solve this problem, but I didn't. I have it. I just forgot to send it to myself and take a picture of it.
Yeah, that's...
That's fine.
Yeah. I guess that's the one problem of these, like, online, you know, submission platforms, isn't it? Gotta take a picture of everything. Yeah.
I'm gonna try to actually go catch the bus, because I think I can make it.
What time?
It'll be here in 7 minutes, but I can make it to the bus.
Oh, yeah, run. Well, I don't know if you should run necessarily, but...
I don't have to run, I just
Yeah.
have to, start my shit.
Yeah. Cool.
I can make it. I can go home.
Party? Or I don't know how big of an actual party it is, but...
Alright. We're just like making. It's like a potluck dinner thing.
Oh, that's fun.
When I say dinner party, I mean like think like wine party and not like undergrads doing a shop party.
Yeah, I remember seeing one of those in the dorms. Yeah, that was.
God, it's too much.
That was
Alright.
yeah. All right, yeah. See ya. Have fun.
Bye. Have fun streaming.
Okay, so now I should be able to track without much issue. There we go. Elsa, welcome back. Oh yeah, you just missed. Yeah, it's one of my colleagues from our research group. They needed to catch the bus, so they left today. They usually called it. They usually come in and then leave at about 4 o'clock. So that's about usually when they leave. But yeah. I guess they're having a potluck or something today. So whatever the case is, yeah. Anyway, cool. So now I can stream earlier. Yeah. Well, I mean, normally I want to stream at this time. I'm just trying it out now, and if IT complains that I'm using too much bandwidth, then yeah, I usually try to do it later in the day. But also, everyone's kind of done for the day. Usually, I have another colleague to the right of me. He has a desk there, but they're usually here until about 5 o'clock. So I usually don't stream until after that. But today, the person that was behind me a moment ago, they were also, we're actually in the same class. so we were talking about the same topic anyway. So I was like, well, if I'm streaming, it's probably not too distracting because at least we're working on the same assignment. Yeah, but anyway, so both of them are gone now for the day. They've called, it's Friday, right? So they've called it a day already. So I figured I'd stream early. I think the guy on the screen is no. See, this guy already has his, is already has a job, right? Unlike me. So actually, so let's see. I think this professor, what's this research on? I want to say they do astrophysics. This professor does astrophysics. Our GSI, or sorry, so the graduate student instructor for our class works with him, and he explained it to me. It's not cosmology, or I can't remember what it was, but oh no, I remember. I think it actually has it's something astrophysics related. I can't quite remember. And specifically right now, I believe they're doing some modeling of certain gravitational waves. I think that's what our GSI is currently working on with this professor. So the way I understand it is that, well, first of all, until very recently, gravitational waves were theorized for about 100 years now, right? But they were only, decisively detected they were only detected really recently. I think he said like 2016 or something. So gravitational wave detection is still a very much very very what do you call it? It's not only is it an active area of research, but there have been significant discoveries in the past several years, right, in that field. So part of that field for detecting these gravitational waves is like either there's kind of two ways you can kind of treat this. The quantum physics guy, I think this is a different professor. This professor does something to do with like astrophysics / cosmology. I'm not quite sure. Sorry, I'll ask the GSI next time I talk to him. But not strictly quantum in the sense that he's not like a Like that's not like there's quantum information now. That's a big field. But he doesn't do strictly like quantum physics or quantum information, but I think it leans more towards cosmology, if anything. This professor on screen right now. Anyway, and one of the things I guess they're working on right now is modeling certain gravitational waves. And by modeling, what they really mean to say is that, studying gravitational waves kind of falls into two broad categories as far as I'm aware. One is the creation of tools to detect the waves, obviously, and then because you need a way to actually see them, right? But then the other side is then predicting, what kind of signal you would get from certain types of waves. And from what I understand, our graduate student instructor, our GSI, is working with this professor specifically for running certain simulations, like to simulate what kind of signal you would get from certain types of, interactions of stuff in space. So which is why I'm pretty sure that this professor is the one that's doing this research, or at least working on this stuff. So that's to say, this is what this professor I think does in terms of like what they're working on, like research wise. So just think like gravitational wave stuff. So it makes sense that this person is teaching electromagnetism and optics, right? Because gravitational waves, so waves in general. So therefore, they should be pretty good at teaching stuff about basic electromagnetic waves, right? So anyway, so that's what we're doing, or that's what I'm studying right now, right? So yeah. But anyway, there's a problem set due tonight, so I want to get through this lecture because I think I'm basically caught up in terms of lectures that are relevant to the current homework assignment, but I want to totally catch up, or I guess not catch up because I have been going to lecture. It's just there's a lot of gaps in my lecture notes, so I want to fill those all in before the end of the weekend. So we'll do that, or that's what we're going to aim for. But today it's going to be finish taking notes for this lecture and then go finish the, or at least write some stuff for the homework. Yeah. New one, welcome back. Or wait, that right? Yeah. Or I don't know what you want to go by. I can't remember, but I think it used to be new one, right? And then I don't. What happened to your old account actually? But anyway, yeah, welcome back. How have you been? Actually, I just realized. Speaking of hands, the camera or the window for the webcam is upside down. I need to fix that later. Yeah. Anyway, yeah. So we're gonna keep taking notes. My throat is dead. Anyway. Excuse me. Yeah. Although part of me wants to go to karaoke. Go karaoke. Anyway. Yeah, no idea. Well, it is what it is. I've lost plenty of accounts too. But yeah, sorry. So today's going to be very much of a focus on studying day, just because. Actually, I'll say, how did your exam go? Because you said you had a history exam today, right? Excuse me. But sorry, yeah. So in general, today's going to be very much a focus on just grinding out, problem sets day. Yeah. Kate, welcome back. It's been a hot minute, I guess. Is that how the phrase goes? I don't remember. But yeah, more studying as same as last time. So feel free to chill or ow or whatever. Yeah, ow. Sleepy must. Yeah, I mean, again, I'm not. For the record, if it seemed like I was trying to like insinuate something, I wasn't. I totally get it. It's not a super convenient time to stream. Of course, I can't really stream. I can't often stream earlier in the day, which it just kind of how it is. But I do realize, like for example, if you live on like the east coast of the U.S., then I basically stream from like midnight or not midnight. I guess I basically I end up streaming from like midnight to like 3 in the morning. So I get for a lot of cases it's not a super convenient time. Um, so don't worry about it. Don't worry about it. Yeah, yeah. I mean, not that you were, but if you were, don't worry about it. It is what it is. That's it just is what it is. Let's see. Mango, welcome back. Quantum mechanics. I mean, I did intro quantum for whatever that's worth, which is not much, right? And Schrodinger's equation. I mean, depends. The time independent one. I mean, yeah, but that's because that's like the basic case, right? Because if you do the time dependent one, then well, there's still approximations and stuff that make it, solvable. But we only essentially what I'm saying is that the intro quantum mechanics course goes over time independent Schrödinger equation solutions, and then in regards to the time dependent ones, it only goes over the kind of the typical approximations. So and often we don't do any. I don't think we. Well, for sure, we didn't do anything above a second order approximation, but most of the time we were pretty satisfied with just like a first order approximation or something. So, yeah, so for whatever that information's worth. Sorry, first and second, for order. So like, by first order and second order approximation, we, so you know how in physics we like linear solutions, so solutions that kind of add on to each other, like it's like what's the best way to phrase this? So let's say your variable is like x, right? So to say, what's the best way to phrase this? At the risk of saying something incorrect, you're gonna have to correct me on this, but my understanding with linear solutions is that it's linear because the solution is a sum of solutions, which is to say, for example, if A is a solution and B is a solution, then for them to be linear in whatever thing you're talking about, then A plus B should also be a solution. So with Schrodinger's equations, or just in general in many fields, right? We like linear solutions because if we can find two solutions, then we can also claim that, or we can say necessarily that the sum of, if they are linear, then we can say that necessarily that their sum is also a solution, which is often very convenient, especially in the case of quantum mechanics, where to construct a general solution, often you use the sum of solutions. You use the sum of a homogeneous and a particular solution to generate a general solution. Squared. Well, no. So A and B can be I mean, so it kind of depends, right? But to say, for example, let's say your variable is like x. Then if a x squared, or sorry, I should stop using a and b, so let's say, well, so essentially let me just get to the approximation. So the approximation, or the order of an approximation is maybe it's easier to talk about like a Taylor series or like a series expansion. I don't know how much math you've done, but if you remember doing like series expansions of stuff in like pre-calc, or I think it's like pre-calc that you do like series expansions. So which is to say, when a number, a certain problem or a certain formula or equation under certain conditions can be so you remember a Taylor series, okay? So, do you remember do you remember all the types of series? Do you remember that there was a type of series where if the number is sufficiently small, then you can kind of break up that, or if the term is sufficiently small, then you can actually break it up into like, if it's like I don't quite remember the form of a Taylor series actually, but you could break up like 1 minus x to the whatever or 1 minus x to like 1 plus x over 2 to the, I think, 2 factorial minus, or what's it, plus? But the point is you could break it up into like this infinite series of terms, right? So when we talk about first, second, or third order approximation, it's essentially doing that type of series expansion, but cutting it off at a certain term. So like a series. So let me. Sorry. So just so I don't talk out of my ass, and just so I can finish talking about this. Let's see, Taylor series. Let me just make sure I have the right equation in my head. Yeah. Here we go. So like in a Taylor series, if you just go to Wikipedia and grab it, for example, right? What is the first order approximation like of a Taylor series? It's essentially I guess let's see. So in Taylor series, would it be just at 1 or 2? I guess it must be. Yeah, it must be the first term. So like, if you look in their example of a Taylor series, where is it? Here. So under examples for Taylor series, and you look at they do a Taylor series of natural log of x, and they talk about how at some point a, and they say how it's natural log a plus 1 over a x minus a minus 1 over a squared, blah, blah, blah. So separate those terms by the plus and minus signs, and then look at how many terms there are. Effectively, it's infinite, right? But the first term is the first term in that approximation is natural log of a, right? And then the second term is 1 over a times x minus a. And then the third term is negative 1 over a squared times quantity in the numerator x minus a, quantity squared divided by 2, and then you could just use the equation at the top to kind of figure out what the remaining terms are. But that goes on infinitely, right? So when you're doing the series, to get a complete solution, you'd have to work infinitely, right? So realistically, all you need to do to get a rough idea of what your solution is, if you're doing this estimation, is you just cut off at a certain term, right? So either the first or second or third term. So when with like the Schrödinger, solving the Schrödinger equation using certain approximations, we're saying at some point we're doing some series expansion, or we're doing some kind of estimation, and that estimation has a bunch of addition. The question is, for each addition, for each term in that big sum of additions, you're getting closer and closer to the exact solution, but it goes on infinitely, so you'll never get there. So for a reasonable estimate of your answer, you just really need to you just need to stop calculating at some point, right? And the number of the order is just, where do you stop calculating your estimation? So first order approximations essentially say we only estimate up to the first term. So if there's some kind of like, under this condition, this can be rewritten as this easier equation, then we essentially only do that estimation to the first term. And then technically, if you kept going, you could make your answer more and more precise. But to say, to nth order is just to say we only go up to this level of estimation. So if you go through a Schrödinger equation and you do like, I think like WKB or something, then you'll see, or even just if you, let's see, what is it? I think like, what is it? What is the equation? It's like if you do the like the energy level stuff, then there's some level of order approximation in there, but you'll see the term first and second order, and that if you look at the derivation, you'll see that that's all they're doing. They're just kind of estimating to a certain point. So for that, I think actually Griffiths was pretty helpful. So if you want to get into the specifics and you haven't looked at Griffiths, I think it's like chapter, what is it? It must be second semester, which I assume is like chapter like 6 and beyond. So if you look at chapter 6 and beyond in Griffiths, then that should be it's Griffiths' Introduction to Quantum Mechanics, I believe, and we used third edition. So if you look up the third edition around like chapter 6 or 7, then you'll see this stuff. Equations are linear if none of the variables are squared. Well, it's the variable can be squared. It's just that you can't have like cross terms of your variables, I guess is to say. So like, x squared plus y squared, where x and y are your variables, that's still linear, but x squared plus xy plus x or plus y squared has a term that contains both x and y, right? So like when you square like x plus y, you get x squared plus x 2xy plus y squared. So that kind of cross term, you've got both of your variables in one term, stuff like that. Though that makes it nonlinear, I believe. Yeah. Don't quote me on this stuff. You need to ask someone that really knows all the math. Are you sure? I'm pretty sure because, if you're asking, am I sure that is the precise technical definition to absolute certainty, then no, I'm not sure. But so then if we assume that you're not allowed to square, if we assume linear means no squares, then I would then ask, how could you possibly have a linear solution that has more than two terms in it, right? Because if you couldn't square your variable at all, then the most terms you could have a solution is your variable and then a constant, right? So, yeah. Yeah. Is that... Well, let me think. I guess this is okay because I kind of wanted a little short break anyway. It's been a long day today. Oh, you know what? I mean linear as in linear solution, not linear as in like a linear function. Is that what we're confused about? That might be it. Okay, no, I see where you're coming from. Sorry, sorry. Are you saying linear like in geometry, like a line? Oh, sorry. No, this is a different. This linear means it's not strictly speaking different, I think, but linear in the context of a solution to a differential equation, which is, yeah, sorry, linear in, yeah, sorry, yeah, no, I thought, no, I should have checked with you first because I realized, that, yeah, no, sorry, yeah, linear in terms of geometry or like, right, you're correct, there are no squares, it's well, what's the best way to explain why that's different? Yeah. Okay. Well, anyway, yeah. Sorry. So you're probably better off. I'm not actually sure why they use the same phrase. I'm assuming that they're related in some sense. But yeah. Sorry. So right. So when a function is linear, then yes, there's just your well, it's called linear because it looks like a fucking line. Yes. When your solution has the property of being linear, or when a set of solutions has the property of being linear, it means that when you add the solutions together, the sum is also a valid solution. So I believe if you this should come up in linear algebra, I guess. In linear algebra, this is how you well, I'm not quite sure, but I do remember, I think the first time you see it is in linear algebra, like intralinear algebra. So that's part of the reason why it's a prereq for taking a differential equations course. But anyway, Yeah, sorry. There's that context. Yeah, sorry. Anyway, yeah. That's all there is to it. Yeah. One of the well, anyway. So you'll see that when studying like, physics. So like linear yeah, exactly. It's a linear combination. That linear. Um, yeah. So it seems like the question has been resolved. I'm going to go back to studying. Actually, let's just say one thing. I'm assuming the linear, like in like geometry, and the linear in like more abstract math, is the same like meaning. I don't know how exactly you derive the fact that the sum of solutions equaling a solution is the same as like drawing a line. So that I defer to YouTube, and well, honestly, that I don't really know how the word developed to mean what it is. So you're gonna have to look that up and figure out that on your own. But so I don't. But which is to say, I don't think that they're strictly separate concepts. My gut feeling is that the word developed into its more generalized definition of meaning the sum of solutions, or having the property of, the sum of solutions also being a solution. I'm assuming that does come from, the fact that you can, a line, has just one variable, right? And you can kind of see that, right? Because let's say that, like the line x, plus 1, for example, that's a line, right? Or f of, the function y equals x plus 1, right? X, so x is just to the first power, right? And then if you squared it, then you'd end up with like a parabola and stuff. Or parabola? Yeah, parabola. But you can imagine, let's say you just defined x to be like the sum of like 300 variables, for example. Then you should still consider it a line, right? But then if x was squared, then all of a sudden you have like variable 1 times variable 1 squared, then variable 1 times variable 2, and then variable 1 times variable 3. And you can see how they're, by replacing the single variable that you were thinking of in your head earlier, like in the case of like geometry and like a line, as soon as you redefine that one variable as like the sum of multiple variables, then you can see how when you start squaring it, you end up with cross terms. So I don't think that they're actually separate concepts. I think that they derive from the same concept. Or I think the whole concept of a linear combination does derive from like just a basic line. I just don't know the exact math for how math developed to come up with that. So, but I'm pretty sure it's not strictly different is all I'm gonna say. Because again, if you took like x plus 1 and then x squared plus 1, and then you just replaced x with like the sum of a ton of variables, like you just redefined x as like a plus b plus c, then you can see how by squaring that entire thing, you end up with cross terms in one case, and in the other case you don't. So yeah. You can tell I'm not a theory math guy, or not even applied math. I'm not math anything. I mean, I guess I know someone that probably knows the answer, but I don't really want to bother him because he's probably busy. What's he doing? Yeah. Yeah, sounds good. Yeah, have fun. What was I doing? Radiation pressure. Okay. And sorry, I know there was a comment earlier in the chat about like someone else said something. Oh, Kate said all this math stuff is hurting my brain. Man, yeah, I mean I can relate. And then new one, why my desk is why I don't know. Is that a question? Why my desk is clean? I don't know. That was about 20 minutes ago, so maybe they're not here anymore. But yeah, and yeah, math is confusing. Linear I did in the winter actually of I can't remember what year, but I did it in in a winter semester in community college, and I took that one class and I still only got a B. I'm pretty proud of that B because it was a hard class for me, but nonetheless, it is to say that I dedicated basically all my time for several months or not several, a few months, and even then, all I could muster was a B. So yeah, math is hard. Math is hard. Oh, actually, I don't know if I'd say I'm proud of a B, but it's the best I could do. I think that's fine. You do what you can. Cool. Excuse me. All right, I gotta go to the bathroom, so I'm just gonna. Also, I gotta go to the bathroom, and then it's about near the end of this lecture thing anyway. So rather than keep the stream going while I go to the bathroom, I'm going to just end it for the moment, and then I'll come back, and then I have to finish more like I have to do as much as I can on the homework or on the problem set. So I'm gonna go get dinner and then come back. So yeah, everyone that came by, thanks for coming by. Take care, stay safe, and I'll see you guys later. Either later as in later today or later as in tomorrow or